Chemical reactions. This chapter discusses the role of chemical reactions in thermodynamics, especially in combustion and energy conversion processes. The main focus is how chemical energy is transformed into heat and work. This topic forms the foundation for analyzing internal combustion engines, gas turbines, and other energy systems. The approach still relies on the first and second laws of thermodynamics. The discussion is consistently linked to mass and energy balances in reacting systems.
Lesson Plan Thermodynamics 2. The course structure shows that chemical reactions come as a logical continuation of power cycles, refrigeration, and gas mixtures. All previous topics serve as the foundation for understanding combustion and chemical reactions. With this sequence, students already have the concepts of energy, enthalpy, and entropy. This chapter integrates all those concepts into a real engineering application. Therefore, chemical reactions represent a culminating application of engineering thermodynamics.
Learning outcome. The learning outcomes emphasize analytical skills rather than mere memorization. Students are expected to balance reactions, calculate combustion parameters, and perform energy balances. In addition, adiabatic flame temperature and entropy change analyses are also highlighted. The second law perspective is introduced to evaluate process quality. This makes combustion understood not only in terms of energy, but also in terms of efficiency and irreversibility. Liquid hydrocarbon fuels. Crude oil distillation separates hydrocarbons based on their boiling points. From one raw material, gasoline, kerosene, diesel, and fuel oil are obtained for different applications. This process shows that fuels are complex mixtures, not single substances. Each fraction has different combustion characteristics and energy content. This is why fuel selection strongly affects the performance of energy systems.
Air composition, oxygen-nitrogen ratio. Air practically consists of 21% oxygen and 79% nitrogen. In calculations, this is expressed as 1 kilomole of O2 accompanied by 3.76 kilomoles of N2. Nitrogen does not participate in the reaction, but it always appears in the products. This ratio becomes the basis of all air-based combustion calculations. Without this understanding, combustion mass balances would not be consistent. Fuel comparison, energy content, and gasoline equivalence. Each fuel has a different volumetric energy content. Gasoline has about 31,850 kilojoules per liter, while CNG is much lower. This table shows that fuel volumes cannot be compared directly without considering energy content. The concept of energy equivalence helps compare the performance of different fuels. This is important for both economic analysis and energy system design.
Check your understanding. Number 1. This part aims to check understanding of fuel energy content. The main focus is recognizing that CNG has the lowest volumetric energy value. Such questions help reinforce intuition about the data in the previous table. No new concept is introduced here. Therefore, this part is skipped in the main discussion.
Steady flow combustion. Reactants in, products out. Combustion is often analyzed as a steady flow system. Fuel and air enter, and products leave continuously. Inside the combustion chamber, chemical reactions change the composition and energy of the flow. This model is highly relevant for gas turbines and boilers. With the steady flow assumption, mass and energy balances become simpler.
Hydrogen-oxygen reaction. Mass conservation. This example shows that 2 kilograms of hydrogen reacts with 16 kilograms of oxygen to form water. The total mass before and after the reaction remains the same. This confirms that the law of conservation of mass always applies to chemical reactions. The reaction equation is simply a stoichiometric representation of this physical fact. This concept is the basis for balancing all combustion reactions.
Air-fuel ratio 17:1. An air-fuel ratio of 17 means 17 kilograms of air is used for every 1 kilogram of fuel. Under this condition, the total product mass becomes 18 kilograms. This directly shows that all incoming mass must leave as products. The air-fuel ratio is a key parameter in combustion analysis. This value strongly affects temperature, efficiency, and emissions.
Complete combustion. Complete combustion occurs when all the fuel reacts perfectly with oxygen. The products consist only of CO2, H2O, nitrogen, and possibly excess oxygen. No unburned fuel remains in the products. This condition represents ideal combustion from a chemical point of view. This concept becomes the reference for defining theoretical combustion and combustion efficiency.
Answer B. The formation of products like CO2, H2O, excess O2, and N2. Explanation of why other answers are wrong. A. The presence of unburned fuel in the products. Incorrect, because unburned fuel indicates incomplete combustion, not complete combustion. C. The production of carbon monoxide and soot particles. Incorrect, because these are byproducts of incomplete combustion, not complete combustion. D. The absence of any products in the combustion chamber. Incorrect, because complete combustion results in specific products like CO2, H2O, and N2, not an absence of products.
Methane combustion. Theoretical balanced reaction. Methane is used as an example of a simple fuel with the formula CH4. In theoretical combustion, the amount of oxygen is exactly sufficient so that no fuel remains and no free oxygen appears in the products. The reaction is written in a stoichiometrically balanced form, including nitrogen from air. This condition is called theoretical or stoichiometric combustion. It becomes the reference point for defining excess or deficient air. ORSAT analyzer, measuring CO2 mole fraction. An ORSAT analyzer is used to measure the composition of combustion exhaust gases. In this example, after CO2 is absorbed, the gas volume decreases from 1 liter to 0.9 liter. From this, the mole fraction of CO2 is calculated as 0.1. This method is based on volume change at the same pressure and temperature. This technique is important for evaluating combustion quality in practice. Microscopic energy. Each molecule has several forms of microscopic energy, such as sensible, latent, chemical, and nuclear. Sensible energy is related to molecular motion and vibration. Chemical energy is stored in atomic bonds, while nuclear energy is stored in the nucleus. In combustion, the most relevant changes are in chemical and sensible energy. This concept explains the origin of heat released in chemical reactions. Chemical bonds and energy release in combustion. Combustion involves breaking old chemical bonds and forming new ones. This process is always accompanied by energy release or absorption. In combustion, energy is released in large amounts as heat. This is the physical reason why chemical reactions can produce high temperatures. In other words, combustion heat comes from the rearrangement of chemical bonds. Check your understanding. Number 3. This part reinforces that heat comes from breaking and forming chemical bonds. Its purpose is to strengthen the link between chemical reactions and energy release. No new concept is introduced here. This question is only a reinforcement of the previous concept. Therefore, this part is skipped in the main flow. CO2 formation, energy release from carbon combustion. This example shows the combustion of 1 kilomole of carbon with 1 kilomole of oxygen.
The reaction produces 1 kilomole of CO2 and releases 393,520 kilojoules of energy. The standard conditions used are 25 degrees Celsius and 1 atm. This energy value indicates how much chemical energy is stored in carbon. It becomes an important reference in reaction energy calculations.
Combustion enthalpy of carbon reacted. For carbon, the value is minus 393,520 kilojoules per k-mole of carbon. The negative sign indicates that energy is released to the surroundings. This quantity is very important for energy analysis of combustion systems. This concept allows systematic calculation of reaction heat.
Enthalpy of formation of CO2. The enthalpy of formation is the enthalpy change when a compound is formed from its elements at standard conditions. For CO2, its value is the same as the enthalpy of combustion of carbon, which is minus 393,520 kilojoules per kmol of CO2. This is because CO2 is formed directly from carbon and oxygen. This concept becomes the basis for calculating reaction heat using formation enthalpy data. In this way, complex reactions can be analyzed systematically. LHV versus HHV. The lower heating value, or LHV, is the energy released when fuel burns with water remaining in vapor form. The higher heating value, or HHV, includes the additional energy from condensing the water vapor into liquid. The main difference between them lies in the latent heat of water vapor. In real engines, LHV is often more relevant because water leaves as vapor. The choice of LHV or HHV strongly affects efficiency calculations. Enthalpy of chemical component. The total enthalpy of a component is expressed as the sum of its enthalpy at a reference state and the sensible enthalpy due to temperature change. The reference state is usually taken at 25 degrees Celsius and 1 atm. With this approach, all reaction energy calculations can be done consistently. Sensible enthalpy represents the part that changes with temperature. This separation simplifies the formulation of energy balances in reacting systems. Answer B. The enthalpy change due to changes in conditions like temperature relative to the baseline. Explanation of why other answers are wrong. A. The enthalpy at 25 degrees Celsius and 1 atm used as a reference state. Incorrect, because this describes the standard enthalpy, not sensible enthalpy. C. The total enthalpy of a component, including its baseline and extra enthalpy contributions. Incorrect, because total enthalpy encompasses both the standard and sensible enthalpy, not just the change due to conditions. D. The baseline enthalpy calculated without considering temperature changes. Incorrect, because this also describes standard enthalpy, not the sensible enthalpy. Internal energy formula. Internal energy can be expressed as U equals H minus PV. By inserting the definition of enthalpy, consisting of standard and sensible parts, this relation becomes more explicit. This formula is important when the analysis is based on internal energy rather than enthalpy. In reacting systems, sometimes one form is more convenient than the other. This relationship ensures consistency between the two approaches. Temperature in complete combustion. The maximum temperature is achieved when combustion is complete and there is no heat loss. This condition is assumed to be adiabatic, so Q equals 0. In this situation, all chemical energy is converted into an increase in the internal energy of the products. This temperature is often called the adiabatic flame temperature. This value represents the upper limit of the temperature that a combustion system can reach. Actual versus theoretical combustion temperature. In real systems, the product temperature is always lower than the theoretical adiabatic temperature. This is caused by heat losses, incomplete combustion, and dissociation.
These factors reduce the energy available to increase the product temperature. As a result, the thermal efficiency of the system also decreases. This comparison is important for understanding the limitations of real systems.
Entropy change in chemical reaction. During a reaction, the system experiences an entropy change expressed as delta S of the system. This change is associated with the transformation of reactants into products. The surroundings are also affected through heat and work interactions. Entropy analysis provides a second-law perspective on combustion. With this, the direction of spontaneity and the irreversibility of the process can be evaluated.
Check your understanding 5. This part reinforces the notation delta S system for entropy change. Its purpose is to strengthen familiarity with the symbol and its physical meaning. No new concept is introduced. This question is just a brief repetition of the previous concept. Therefore, this part is skipped in the main discussion. Entropy adjustment for ideal gases. The entropy of an ideal gas at different pressures can be calculated by correcting the tabulated value at the reference pressure. In this way, the absolute entropy can be determined at various operating conditions. This approach is very important in analyzing reactions involving pressure changes. This formula ensures that entropy calculations remain thermodynamically consistent. Without this correction, second-law analyses would be inaccurate. Exergy difference. The exergy difference between reactants and products represents the maximum theoretical work that can be obtained. The reactants have higher exergy than the products. During the reaction, part of this work potential is destroyed due to irreversibilities. This concept links chemical reactions to the fundamental performance limits of systems. With exergy analysis, the quality of energy conversion can be evaluated, not just the quantity. Gibbs function of CO2 formation. The formation of CO2 from carbon and oxygen at 25 degrees Celsius and 1 atmosphere can be analyzed using the Gibbs function. The negative value of the Gibbs function of formation represents the maximum reversible work obtainable from the reaction. For this reaction, the value is about 394,360 kilojoules per kilomole. This quantity is slightly different from enthalpy because it already accounts for entropy effects. This concept links chemical reactions to the theoretical limit of converting energy into work. Answer C. The maximum reversible work obtainable from the reaction. Explanation of why other answers are wrong. A. The heat released during the reaction. Incorrect, because the negative Gibbs function represents work, not heat, though they are related thermodynamically. B. The energy required to initiate the reaction. Incorrect, because the Gibbs function does not describe activation energy, but rather the maximum work potential of the reaction. D. The equilibrium constant for the reaction. Incorrect, because while the Gibbs function can relate to equilibrium, it directly represents the maximum reversible work, not the equilibrium constant. References. All figures are taken from the book by Chengel, Bowles, and Konolu. This reference is one of the main textbooks in engineering thermodynamics. It confirms that the material follows well-established international standards. Students can refer directly to the book for deeper study. Thus, this lecture material has a strong scientific foundation.